The Milky Way is still making stars. Not many, not at the rate it once did. But somewhere in the dense molecular clouds threading through the spiral arms, gravity is still doing what it has always done, pulling hydrogen together until pressure and temperature cross a threshold, and fusion begins. A new star ignites. It will burn for millions, or billions, or in some cases trillions of years, depending on its mass, and then it will stop. What we rarely think about is that this process has a budget. The Milky Way contains a finite amount of raw material, gas, dust, the molecular reservoirs that gravity can compress into stellar nurseries. That budget is not being replenished at the rate it is being spent. Every star that forms locks away a portion of the galaxy's remaining hydrogen. Every supernova scatters some of it beyond recovery. The galaxy is not a machine running on an infinite fuel supply. It is running down. The current star formation rate in the Milky Way sits somewhere around 1 to 3 solar masses per year. That sounds productive until you set it against what the galaxy was doing in its early history, when the rate was 10 to 20 times higher. The peak of star formation, the era when the galaxy was building most of its stellar population in great surging waves, happened roughly 10 billion years ago. We are living in the long tail of that process. The construction phase is mostly finished. What remains is the slow consumption of what is left. Astronomers estimate that the Milky Way's remaining cold gas reservoir, the raw material for new stars, amounts to somewhere between 5 and 10 billion solar masses. That sounds enormous, and it is by any human measure. But the galaxy has already converted hundreds of billions of solar masses into stars over its lifetime. The fraction left is modest. At current formation rates, and accounting for the fact that not all of that gas is in a form that can efficiently collapse, the Milky Way has enough material to continue forming stars for perhaps a few billion more years at meaningful rates. After that, the pace slows towards something closer to occasional than continuous. This is not a crisis in any immediate sense. The sun will exhaust its own hydrogen fuel in roughly 5 billion years, long before the galaxy's last star forms. Most of the stars burning in the Milky Way today will outlive the sun by comfortable margins. The low-mass red dwarfs, the dim and patient stars that make up the majority of the galaxy's stellar population by number, will still be fusing hydrogen long after the sun has swelled into a red giant and collapsed into a white dwarf. Some of them will burn for trillions of years. But this is precisely where the picture becomes harder to hold in the mind comfortably. The stars that will survive the longest are not the stars we see most easily. They are not the bright giants that dominate the night sky, not the blue and white stars that define the familiar constellations. Those are brief candles by stellar standards, burning through their fuel in tens or hundreds of millions of years before exploding or collapsing. The long-lived stars are the smallest and dimmest red dwarfs with masses a fraction of the sun's, burning so slowly that their fuel lasts not billions but trillions of years. The universe is currently only 13.8 billion years old. The longest-lived red dwarfs have barely begun their lives. So the Milky Way's future is not simply darkness arriving on a predictable schedule. It is a long, slow transition. The bright stars die first. The spiral arms fade. The star-forming regions exhaust their gas and go quiet. What remains is an aging population of increasingly dim survivors. The red dwarfs burning at low temperature, contributing almost nothing to the galaxy's overall luminosity, but persisting long after every other stellar type has gone cold. The galaxy does not switch off like a light. It dims and dims and dims across timescales that make the current age of the universe look like the opening seconds of a very long story. What drives this transition is not dramatic. It is not a collision, not an explosion, not a catastrophic event. It is something quieter and in some ways harder to fully absorb. The galaxy is running out of the conditions that make stars. Gas cools, fragments, collapses, but only if there is gas available. and only if the conditions allow it. As the remaining molecular clouds are consumed, as the galaxy's disk becomes increasingly dominated by stellar remnants rather than active stars, the opportunities for new star formation become rarer. The galaxy does not die. It exhausts itself. The question worth sitting with is not when the last star forms. The question is what it means that we exist in the era when the galaxy is still, by cosmic standards, relatively young and active. The fact that life emerged on a planet orbiting a middle-aged star in a galaxy still capable of producing new stars, in a universe still dense with the warm light of active stellar fusion, that timing is not guaranteed. It is a condition, and conditions change. To understand what the galaxy is losing, it helps to understand what stars actually do. The obvious answer is that they produce light and heat. But that description undersells the role stars play in the chemical architecture of everything that exists. The Milky Way began as a cloud of hydrogen and helium, the two lightest elements, forged in the first minutes after the Big Bang. Nearly everything heavier than that was made inside stars: carbon, oxygen, nitrogen, iron, calcium, silicon, the elements that build planets, oceans, atmospheres, and biology. None of them existed in meaningful quantities before the first generation of stars lived and died. Stars are not just sources of energy. They are the universe's primary mechanism for chemical complexity. The process works through a chain of increasing pressure and temperature. In the core of a star like the Sun, hydrogen fuses into helium. In more massive stars, helium eventually fuses into carbon and oxygen. Push the pressure higher, add more mass, and the chain continues: neon, magnesium, silicon, sulfur, all the way to iron. Iron is where the chain stops. Fusing iron absorbs energy rather than releasing it, and a star that reaches an iron core has reached the end of its ability to generate outward pressure through fusion. What follows in the most massive stars is collapse and explosion, a supernova that scatters the accumulated heavy elements across the surrounding interstellar medium. Those elements become the raw material for the next generation of stars, and for the planets that form around them, and, under the right conditions, for chemistry complex enough to organize itself into something that can ask questions about where it came from. This recycling process is one of the defining features of the galaxy's history. Each generation of stars enriched the interstellar medium with heavier elements. Each generation of planets formed from a slightly more chemically complex starting point. The first stars, the population known as Population 3, which no one has directly observed, but whose existence is strongly implied by the physics, formed from nearly pure hydrogen and helium. They were massive, brief, and their deaths seeded the galaxy with the first heavy elements. The stars that followed, and the stars that followed those, built on that inheritance. The Sun is a third-generation star, or close to it. Its composition reflects billions of years of stellar processing before it ever ignited. What this means for the galaxy's future is that the chemical enrichment process is also winding down. New stars still form, and their eventual deaths will contribute further heavy elements to the interstellar medium. But as star formation slows, the rate of chemical enrichment slows with it. The galaxy is not becoming more chemically complex over time at the rate it once was. The era of rapid elemental buildup, the era that produced the conditions for rocky planets and liquid water and carbon chemistry, was concentrated in the galaxy's past. We are the product of that era. The stars still forming today are born into an already mature environment. The stars that form in the far future, if they do, will inherit whatever remains. There is another piece of this picture that rarely gets the attention it deserves. Stars do not just enrich the interstellar medium through their deaths, they regulate it through their lives. The ultraviolet radiation from massive stars ionizes surrounding gas, creating the glowing nebulae visible throughout the galaxy's spiral arms. The stellar winds from active stars push material around, creating pressure waves that can trigger new rounds of star formation in adjacent molecular clouds. Supernovae drive turbulence through the interstellar medium on scales of hundreds of light years. The galaxy's star-forming activity is partly self-sustaining. Active stars help create the conditions for the generation. As that activity declines, the feedback weakens. Fewer massive stars means less ultraviolet radiation driving ionization. Less turbulence means molecular clouds can stagnate rather than fragment efficiently. The galaxy's ability to convert raw gas into new stars depends partly on the dynamism generated by its existing stellar population. When that population ages and the most energetic stars are gone, the star-forming engine loses some of the mechanisms that kept it running. The Milky Way's spiral structure itself is a product of this dynamism. The spiral arms are not fixed features, they are density waves, regions where gas and stars pile up and interact, where star formation is concentrated. As the galaxy's gas reservoir depletes and the stellar population ages, the spiral structure will gradually fade. The galaxy will become more uniform, more settled, more like the elliptical galaxies that have already exhausted their star-forming gas galaxies, whose blue spiral arms have faded into a uniform reddish glow of aging, low-mass stars. That transition has already happened to many of the large galaxies visible in deep field surveys. Elliptical galaxies are often described as red and dead, a phrase that sounds more dramatic than the reality, which is simply their star-forming era ended earlier than ours. They ran through their gas faster, perhaps through more vigorous early star formation, or through galactic mergers that heated and expelled the cold gas needed for new stars. What remains is the long-lived population of low-mass stars, glowing dimly and steadily, producing no new generations. The Milky Way is not there yet, but the direction is not uncertain. The stars currently lighting the galaxy's spiral arms are spending down a reserve that will not be fully replenished. The chemical factory that built the conditions for planets and life ran its most productive shifts long before the sun formed. What we are living through is not the peak of the galaxy's story. It is somewhere in the middle chapters, past the most active phase, still warm and lit, but already past the moment when the most was being made. The last star the Milky Way ever forms will almost certainly be a red dwarf. This is not a guess. It follows directly from the physics of star formation. As the galaxy's gas reservoir depletes and the remaining molecular clouds become thinner and less dense, the conditions that produce massive, luminous stars become increasingly rare. Massive stars require dense, high-pressure cores to ignite. They are the product of violent, concentrated collapse events in rich molecular clouds. As those clouds thin out over billions of years, the collapses that still occur will tend to be smaller, producing lower-mass stars. The galaxy's final stellar generations will be weighted heavily toward the dim end of the mass spectrum. Red dwarfs, stars with masses ranging from about 8% to roughly 50% of the Sun's mass, are already the most common type of star in the Milky Way. Estimates suggest they account for somewhere between 70 and 80% of all stars in the galaxy. They are so dim that not a single one is visible to the naked eye from Earth, despite the nearest star to the Sun, Proxima Centauri, being a red dwarf located just over 4 light-years away. Their luminosity is a fraction of a percent to a few percent of the Sun's output. They burn cool and slow, and they last an extraordinarily long time as a result. The longest-lived red dwarfs, the smallest ones near the bottom of the stellar mass range, have calculated lifespans of 1 to 10 trillion years. The universe is currently 13.8 billion years old. A trillion years is roughly 70 times the current age of the universe. The smallest red dwarfs have not yet lived through anything close to a significant fraction of their total lifespan. They are, in the most literal sense, just getting started. This creates a strange asymmetry in the galaxy's future population. The stars that dominate the sky today, the sun-like stars, the giants. The bright blue stars of the spiral arms are temporary features on the timescale of the galaxy's full lifespan. They will be gone, most of them, within the next few billion to few tens of billions of years. What replaces them in the galaxy's census, and what eventually dominates, is the slow red glow of the dwarf population. The galaxy's old age will be lit, to the extent it is lit at all, by stars that are barely bright enough to qualify as stars by the standards we are used to. For a long time, astronomers assumed red dwarfs were poor candidates for hosting life. The reasoning was straightforward. They are dim, so a planet warm enough to support liquid water would need to orbit very close to the star. At that distance, tidal forces would likely lock the planet's rotation to its orbital period, leaving one face in permanent daylight and the other in permanent night. The stellar activity of young red dwarfs is also intense flares and ultraviolet bursts that could strip atmospheres or damage complex chemistry before it had a chance to stabilize. The picture was not encouraging. That picture has become more complicated in recent years. The question of whether tidally locked planets can maintain habitable conditions is no longer settled in the negative. Atmospheric circulation models suggest that a thick enough atmosphere might distribute heat sufficiently between the day and night sides to prevent the temperature extremes that would make liquid water impossible. The flare problem is real, but it may be a filter rather than an absolute barrier. Planets with magnetic fields, with sufficient atmospheric depth, with the right chemical buffering, might survive the active phase of a young red dwarf and find stability afterward. None of this confirms habitability. It removes the easy dismissal. The reason this matters for the galaxy's long-term story is that red dwarfs represent the overwhelming majority of the time the Milky Way will spend as a star-bearing system. If the conditions around red dwarfs can support complexity, biological, chemical, or some form we have not considered, then the galaxy's productive era, in terms of hosting anything organized enough to matter, may not be behind us. It may be mostly ahead. This is one of the more disorienting possibilities in the long-term picture of the galaxy. The conventional assumption is that the peak of the Milky Way's habitability corresponds roughly to its peak star. Forming activity, the era of sun-like stars, rocky planets in comfortable orbits, stable ultraviolet environments. That era produced us. But it is a narrow window compared to the trillion-year stretches during which red dwarfs will quietly burn. If life can find a foothold around those stars, then the galaxy's biological potential, whatever that means, and the uncertainty is real, is concentrated, not in its past, but in its deep future. The counter-argument is also worth holding. Red dwarf planets face challenges that may be insurmountable in practice, even if they are not insurmountable in principle. The flare problem during early stellar evolution is severe. Tidal locking creates atmospheric dynamics with no analog in the environments where life is known to work. The dim, red-shifted light of a red dwarf may interact differently with photosynthetic chemistry. The argument that life can adapt to these conditions is not wrong, but it is also not proven. We have exactly one example of life arising, and it did not arise around a red dwarf. What the existence of red dwarfs does establish without ambiguity is a timeline. The Milky Way stellar era, the period during which it contains burning stars, energy gradients, and the thermodynamic conditions that allow complex organized processes, extends far beyond anything the current age of the universe might suggest. The last red dwarf will not exhaust its hydrogen for trillions of years. Until that moment, the galaxy will not be dark. It will be dim and cooling and aging, but not dark. The darkness comes after. When the last red dwarf exhausts its hydrogen, something specific happens. Unlike the sun, which will swell into a red giant as it leaves the main sequence, the smallest red dwarfs are predicted to go out more quietly. They are fully convective, meaning hydrogen is continuously mixed throughout the entire star, not just in the core. allowing them to consume a much larger fraction of their total fuel than stars like the Sun can. When the fuel is finally gone, they do not expand dramatically, they contract. They fade. They become white dwarfs, dense, slowly cooling remnants, roughly the size of Earth, but containing a mass comparable to the Sun, no longer generating energy through fusion, radiating only the thermal energy accumulated over their long lives. White dwarfs cool slowly, extremely slowly. The timescale for a white dwarf to radiate away enough heat to become effectively cold, what theorists call a black dwarf, is longer than the current age of the universe by many orders of magnitude. Calculations suggest it would take somewhere on the order of 10 to the 15th power years, a quadrillion years, before the hottest white dwarfs cool to temperatures near absolute zero. At that point, if the proton is stable, and there's a genuine uncertainty about this, what remains is an inert, cold, dark crystalline mass, a black dwarf, an object that was once a star, that once warmed planets and drove chemistry, now indistinguishable from the surrounding darkness except by its mass. No black dwarfs exist yet. The universe has not been around long enough to produce one. Every white dwarf currently observable is still radiating, still a faint source of energy in a cooling cosmos. But their eventual fate is not in serious dispute. The heat will leave, the light will stop. What remains will be cold and dark and very nearly inert. This is the galaxy's long-term population. Not stars, but their remnants. White dwarfs becoming black dwarfs. Neutron stars, the dense collapsed cores of massive stars that exploded as supernovae, slowly cooling in the dark. Stellar mass black holes, carrying the mass of stars that once burned, but contributing nothing to the surrounding environment except gravity. And in the center, the supermassive black hole at the galaxy's core. Sagittarius A, currently 4 million solar masses persisting long after the last star has gone cold, holding the remnant galaxy together by gravity alone. The galaxy does not disappear when the stars go out. Its mass remains. Its structure, loosened over trillions of years by gravitational interactions, that slowly eject stars and stellar remnants into intergalactic space, persists in degraded form. The black hole at the center grows slowly as it absorbs infalling material. Though with no gas left to form accretion disks, its activity drops to nearly nothing. The gravitational interactions between stellar remnants continue to reshape the distribution of mass on timescales that stretch beyond any intuitive frame of reference. Eventually, on timescales of 10 to the 23rd power years or longer, gravitational interactions will have ejected most of the galaxy's mass into the intergalactic void. What remains will be the central black hole, alone, surrounded by a sparse halo of the remnants that did not escape. Even that is not the end. Black holes themselves are not permanent, at least not according to the physics worked out by Stephen Hawking in the 1970s. Through a quantum mechanical process, black holes slowly radiate energy. The rate is inversely proportional to their mass. Smaller black holes radiate faster. Larger ones radiate so slowly that the process is completely undetectable against the background of the current universe. But given enough time, even a supermassive black hole will evaporate. The timescale for a black hole of Sagittarius' current mass to evaporate completely through Hawking radiation is approximately 10 to the 87th power years. That number is so large it resists comparison. The age of the universe is 10 to the 10th power years. The difference between those two exponents is not a matter of degree. It is a difference in kind. After the black hole evaporates, what remains is the low energy radiation it produced. During that process, a faint wash of photons spreading outward into an expanding, cooling universe. The mass that was once the Milky Way, the hundreds of billions of stars, the clouds and nebulae and planetary systems, and whatever organized chemistry they may have hosted, has been converted to diffuse radiation spreading across a cosmos so old and so cold that no structure capable of detecting it could plausibly exist. This is not speculation dressed up as science. Each step in that chain follows from physics that is either well established or, in the case of Hawking radiation, theoretically robust, even if not yet directly confirmed. The uncertainty is not about whether these things will happen. The uncertainty is about the finer details of timing and about whether processes not yet understood, proton decay, vacuum decay, phenomena outside current models, might alter the picture in ways that are currently invisible to us. What is worth pausing on is the structure of that timeline. The galaxy's star-forming era, the period from its earliest stellar generations to the exhaustion of the last red dwarf, spans perhaps 15 to 20 trillion years, from start to finish. The era of cooling white dwarfs and black dwarf formation extends perhaps a quadrillion years beyond that. The era of black hole evaporation extends further still by dozens of orders of magnitude. And the Milky Way's current age, 13 billion years, sits so close to the beginning of this full timeline that describing it as early would be an understatement. We are not in the middle of the galaxy's story. We are in the first breath of it. And the conditions that produced us active star formation, heavy element enrichment, warm rocky planets orbiting stable stars, are features of that first breath, not of the long ages that follow. There is a question embedded in all of this that tends to get avoided because it has no comfortable answer. If the galaxy's productive era, the era of active star formation, chemical enrichment, rocky planets, stable stellar environments, occupies such a narrow slice of the full timeline, why did life emerge when it did? The question sounds almost theological, which is part of why it makes physicists uncomfortable. But it has a scientific framing, and that framing is worth taking seriously. The anthropic principle, in its weakest and most defensible form, simply observes that any observer capable of asking questions about the universe must exist conditions that permit observers to exist. This sounds circular, and in a sense it is, but it carries a real implication. We should not be surprised to find ourselves in an era when the conditions for complexity are available, because we could not exist in an era when they are not. The observation selects for the conditions. The conditions do not select for the observation. This reasoning explains why we exist in the stellar era rather than in the cold darkness of the far future. It does not explain why we exist now, in this particular century, on this particular planet, rather than at some other point within the stellar era. The stellar era spans trillions of years. Our civilization is a few thousand years old. The probability that a randomly selected observer within the stellar era would find themselves at this specific moment, rather than at some point in the vastly longer red dwarf phase, is extraordinarily small. Some researchers have taken this timing seriously as a constraint. A 2016 analysis led by astrophysicist David Kipping and colleagues at Harvard examined the question of whether the emergence of life around sun-like stars versus red dwarf stars could be evaluated probabilistically. The core tension is this: sun-like stars are rarer and shorter-lived, but they offer a more immediately hospitable environment. Red dwarfs are overwhelmingly more common and far longer-lived, but their habitability is uncertain. If the probability of life emerging around a red dwarf is even a small fraction of the probability around a sun-like star, the sheer numerical and temporal dominance of red dwarfs means that a randomly selected observer in the galaxy should, statistically, be more likely to find themselves around a red dwarf than around a sun-like star. The fact that we orbit a sun-like star therefore requires some explanation. One possibility is that we are genuinely unusual, that the conditions around sun-like stars are significantly more favorable for complex life, enough to outweigh the numerical advantage of red dwarfs. Another possibility is that we are early, that the emergence of complex life around red dwarfs is possible but has not yet had time to occur, because the universe is still young and the red dwarf era has barely begun. Under this interpretation, most observers in the galaxy's full history have not yet been born. We are among the first, not the typical. A third possibility, less discussed but not unreasonable, is that the red dwarf environment poses barriers that are not merely challenging, but prohibitive, that tidal locking, flare activity, or some other factor not yet fully characterized, makes complex life around red dwarfs essentially impossible in practice. Under this interpretation, the stellar era is not as long as the physics suggests in terms of its biological potential. The window for life closes when the sun-like stars go out, not when the red dwarfs finally exhaust their fuel. The long red dwarf age would then be biologically empty, a vast, dim, cold to the only era when anything organized enough to matter could exist. If that is true, the timeline compresses dramatically. The window for life in the Milky Way is not 15 trillion years. It is closer to the lives of sun's light, a few tens of billions of years from the formation of the first rocky planets around metal-enriched stars to the death of the last sun-like star. The galaxy's chemical history suggests that window opened perhaps 8 to 10 billion years ago, as the interstellar medium became enriched enough to form rocky planets with the right elemental composition. The sun formed about 4.5 billion years ago. Near the middle of that window, the last sun-like stars will burn out in another 5 to 6 billion years. We are, by this framing, close to the middle of the only era that matters for life, as we understand it. That does not mean the red dwarf question is settled. The honest position is that it is not. Exoplanet surveys have identified numerous rocky planets in the habitable zones of red dwarfs. The TRAPPIST-1 system, a red dwarf star roughly 40 light-years from Earth, hosts at least 3 planets in or near the habitable zone. Whether any of them have atmospheres, liquid, water, or chemistry of any kind remains unknown. The James Webb Space Telescope has begun probing TRAPPIST-1 planetary atmospheres, and the results so far are inconclusive rather than encouraging or discouraging. The data needed to answer the red dwarf habitability question definitively does not yet exist. What does exist is the asymmetry. The galaxy's future is overwhelmingly red dwarf dominated. The conditions we exist in warm, chemically rich, orbiting a bright, stable star in an era of active galactic star formation are not representative of the galaxy's typical state across its full timeline. They are representative of a specific phase, a phase that is already past its peak and moving slowly, but without reversal, towards something colder and dimmer and quieter. The galaxy is not dying. That framing imports too much drama into a process that is fundamentally about depletion rather than catastrophe. It is aging. Its most productive and chemically dynamic era is behind it. The conditions that assembled the raw material for planets, atmospheres, oceans, and biology were concentrated in the past. What lies ahead is a long, slow dimming, punctuated by the quiet persistence of stars, too small and too patient to hurry. Whether anything in that long dimming can use what remains is the question the galaxy's future holds open. And it is not a question the galaxy will answer on any timescale that connects to us. The Milky Way will outlast everything familiar about it. That is perhaps the most difficult part of this picture to hold clearly. When astronomers describe the galaxy's future, they are not describing a place that resembles anything we would recognize. The spiral arms will fade. The star-forming regions will go quiet. The bright blue and white stars that define the visual texture of the galaxy today will be gone, replaced first by an aging population of orange and yellow stars, then by the dim red glow of the dwarf survivors, then by nothing that produces light in any wavelength a human eye could detect. The structure persists, held together by gravity, but the activity that gives the galaxy its current character, the turbulence, the radiation, the chemical cycling, the constant construction of new stellar systems, winds down over timescales that make the current age of the universe seem like a prologue. There is something specific about this that resists easy absorption. We tend to think of the galaxy as a backdrop, a setting, the environment within which the story of planets and life and civilization unfolds. But the galaxy is not a stable backdrop. It is a process. It has a beginning, a peak, and an endpoint. It formed, it accumulated gas and built stars. It enriched its interstellar medium through generations of stellar death. It produced the conditions for rocky planets and complex chemistry. And it is now, slowly, spending down the reserves that made all of that possible. The backdrop is changing. It has always been changing. We exist at a particular point in that change, and the direction of the change is not toward more of what produced us. This is where the deep time picture becomes genuinely hard to situate ourselves within. Human civilization is perhaps 10,000 years old, generously. The scientific tradition that produced the telescopes and the physics to understand the galaxy timeline is a few centuries old. Set against the tens of billions of years the galaxy has already existed. And the trillions of years it will continue to exist in diminished form. The entire span of human history and knowledge is not even a rounding error. It is below the resolution of any timeline drawn to scale. And yet, from within that vanishingly brief moment, we have somehow reconstructed the full arc, from the first stars to the last black dwarf, from the peak of star formation to the eventual evaporations of the central black hole. That reconstruction is either one of the most remarkable things a physical process has ever done, or it is so common across the galaxy's history that it barely registers as unusual. We do not know which. We have no way to determine, from the information currently available, whether the emergence of a civilization capable of understanding its own cosmic context has happened once in the Milky Way, or 1,000 times, or never before us. The silence of the galaxy, the absence of any confirmed signal, any unambiguous techno-signature, any clear evidence of another civilization's presence across the billions of years and hundreds of billions of stars that preceded us does not answer the question. It deepens it. What we can say is that the conditions that produced us are not permanent features of the galaxy. They are phase-dependent. The chemical enrichment required to build rocky planets with the right elemental ratios took billions of years to accumulate. The stable stellar environments that allow planetary systems to persist long enough for complex chemistry to develop are a product of the current era's mix of stellar masses and interstellar conditions. The galaxy's future will have stars for a very long time, but they will be different stars in a different environment. And whether those differences matter for the emergence of complexity is a question we are not yet equipped to answer. There is a version of this picture that is almost consoling. The red dwarf era stretches ahead for trillions of years. If life can work in those environments, the galaxy's biological future dwarfs its biological past. Whatever produced us may have produced only the first chapter of a much longer story. The conditions we think of as necessary may turn out to be merely the conditions we are familiar with. Life, if it is robust enough and flexible enough, might find the red dwarf era not a closing door, but an opening one. But that consolation requires an assumption we cannot currently support. It requires that the transition from chemistry to biology to complexity is not so narrowly dependent on conditions like ours that it fails everywhere else. And we have no evidence bearing on that question. We have one example. It happened here. It happened in this era. It happened around this kind of star. We do not know if it was easy or hard, common or rare, early or late, relative to whatever distribution of such events the galaxy might eventually produce. What the galaxy's timeline does is remove the assumption of permanence. The conditions that feel like the natural state of things, a lit sky, a warm planet, a star that rises and sets with reassuring consistency, are not the natural state of the galaxy. They are a window. The galaxy spent billions of years building toward them, and will spend trillions of years moving past them. The window is open now. It will not always be. The last star the Milky Way ever forms is out there somewhere in the future, in a molecular cloud that does not yet exist. From gas that has not yet been compressed by the right gravitational interaction at the right moment. It will be small. It will be dim. It will burn for longer than the current age of the universe many times over. And when it finally exhausts its fuel and fades, the galaxy will continue dark, cold, massive, and silent 4 times scales that make its entire stellar history look like the first few seconds of a story told over an almost unimaginable length of time. The question is not whether that ending comes. The physics is clear enough on that. The question is what the long darkness means for the brief, warm, lit moment we happen to occupy, and whether anything in the trillions of years that follow will ever look back at this era and recognize it as the time when the galaxy was still alive. We do not know, and the galaxy will not wait for us to find out.